So I'm going to talk about electron dynamics, by which I mean using inelastic X-ray scattering to look at the way electrons, the excitations electrons have in solids. And the subtitle here is From Electron Volts to Picoseconds. So I'm going to give you a bit of history of the technique as I go through. The first experiments we did in this field, we had sort of an EV-type energy resolution. As I'll show you, that evolved dramatically over the time that I've been involved in and others, to now as we're measuring our energy resolutions in millivolts, which is really exciting. And so responding to Stephen's comment about having too many counts, once you get too many counts, you try and do something different. In this case, we try to do time-resolved inelastic X-ray scattering. And so that's the experiment I'll tell you about today. So that's kind of where we're going. There's an outline to the talk, so I'll start with a general introduction to excitations and why we care about them in solids. I'll try and keep that pretty simple. And then the technique of inelastic X-ray scattering. Again, this will be just a general introduction. And as I said, I want to go through some of the history of the field because APS has been a big part of that, and I wanted to remember that and go through that with you guys here. And then the experiment I'll talk about is looking at how a particular set of excitations, spin waves, and I'll explain about those when I get there, how spin waves evolve when you excite a system with a pump pulse. So we're going to hit the system with a infrared pump in this case, and then watch it evolve in time, watch the inelastic spectrum evolve with time. And then at the end, I'm going to say a few words about where inelastic X-ray scattering might be going in the near future. I'm not going to get too speculative here. OK, so I wanted to acknowledge all my collaborators in this work first. This is not all my collaborators. This is just the people involved in the one experiment I'm going to talk about. I'll be showing you data throughout the talk from all kinds of people, and so I want to acknowledge them up front. This is just the people involved in the time-resolved work done at the FELs. We did one experiment at Sackler and one experiment at the LCLS. And just to give you a sense that these teams are no longer the few individuals it takes to run a synchrotron experiment. Now they're massive teams because of the wide range of skills you need to get to make one of these experiments work. So they range from preparing the sample, from running the spectrometer, from running the data analysis system, to running the laser, to organizing this team together. It's a huge operation. It takes many people to make the whole thing work, and all these people were essential in making the experiment the success it was. So it's also been kind of fun working such a large team on one project. So I must say that was a nice change. All right, so let's start at the beginning. Why do we care about excitations? Well, I'll try and argue that in order to be able to claim you understand your system, you need to understand not just the ground state, not just the static structure of the system, but the excitations as well. If you're a high-energy physicist, you talk about in the language of a vacuum state and the particles that exist within that vacuum. So your quarks or your gluons or whatever. In condensed matter physics, we're lucky. We have many different vacuum states. You could be a ferromagnet or a superconductor. Each has its own spectrum of particles, its own set of excitations, and they determine the properties of that state. So you really need to understand them well. And that's not limited to condensed matter physics. So biologists talk about the normal modes of a protein. The way a protein vibrates or fluctuates or moves goes a long way to determine its function. It's not just its static structure. So understanding the excitations of systems is really important in understanding their functional properties. So I'm going to talk about a class of materials today called strongly correlated electron systems. These are typically insulators. And this is a cartoon diagram of the excitation spectrum of one of those systems. So if we start from the low energy excitations, so the phonons, these are the lattice vibrations. These are some of the lowest energy excitations you might see. There are the magnons there. These are the spin excitations. And I'm going to spend a lot of time talking about magnons, so I'll introduce those to you in a bit more detail in a minute. In these systems, they extend maybe up to a few hundred millivolts, something like that. These are insulators, so then there's a big charge gap. And then you start to see the charge transfer excitations at the high energies of order 1 or 2 eV or so. That's the excitation that defines the insulating properties of these materials. That's the optical excitation. So in the cuprates, for example, that's at 2 eV. That's moving charge from an oxygen site onto a copper site. And then there are these orbital excitations, or crystal field excitations, or DD excitations. They all have different names for the same thing. These are moving one electron from one orbital to another orbital. So they're charge neutral excitations, and they typically exist around an eV or so. And again, these excitations and this whole spectrum of excitations determines the dynamic response of the system. You can calculate the response function of the material if you know that excitation spectrum. So it's a very important thing to understand. In addition, some of these excitations can create new phenomena in the material. So the famous example of this is superconductivity, which is driven by pairing of electrons mediated by phonons. So it's another reason to understand what your excitation spectrum looks like. And there are theories of high temperature superconductivity which are mediated by the magnon. So again, you care about that. And then the final motivation here is that the excitation spectrum provides a very stringent test of any theoretical description you might have. So it's one thing for your theory to predict the ground state. That's already hard enough in many of these materials. But if you can predict the ground state and the excitation spectrum, well, then you know you're in pretty good hands. So that's kind of the final motivation for why we look at these things. And the point is that inelastic X-ray scattering can now study all these excitations over the relevant regimes of momentum and energy transfer that you care about in condensed matter systems. That's not a statement you could have made 10 years ago. It's only the last few years we've been able to study this whole slew of excitations, in particular these low-energy excitations, the magnons and the phonons. Okay, so I want to talk a lot about magnons. So I'll just, for those of you who are not familiar, just give you a cartoon diagram of what a magnon is so you have a picture in your head. And so I'm going to start with a very simple system. So this is a one-dimensional array of spins. So think of these as spin one-half objects. And this is the Hamiltonian that describes this model. So this is a one-dimensional Hamiltonian with the nearest neighbor coupling J. And the ground state of that system is a ferromagnet with all the spins pointing up. So that's our vacuum state, if you like. And then you ask, okay, what's the excitation? What's the first excitation that's possible on this vacuum? What's the first particle that we could create? Well, you say, well, let's just flip one spin. So you've taken a plus half and turned it into a minus a half. So it's an excitation with delta S of 1. But it turns out this is not an eigenstate of this Hamiltonian. This is not the lowest low energy excitation you can create. You can think of a lower energy excitation if you take the same delta S of 1 and smear it out across a number of different sites. So this is a superposition of different states with this delta S on each different site. And so you can think about this as a slight tilting of each spin, slightly off normal, if you like. And this delta S then processes through the solid with some wavelength, lambda, and that's given by 2 pi over q. And the energy of this excitation just depends on that wavelength. And you can calculate the energy if you know your Hamiltonian. And that's the so-called dispersion relation. That's the energy of your excitation as a function of wavelength. And so for this particular model, here's the dispersion relation. It's just a sinusoidal dependence of the energy against momentum transfer or inverse wavelength, if you like. And the point is then that this dispersion relation, there is a direct connection between the dispersion relation and the underlying Hamiltonian of your system. So if you can measure your dispersion relation, you can extract from that the Hamiltonian system, and that describes all the low-energy dynamics of your material. So that's a really important object in studying any material. And neutrons have made their living on this for years now by measuring dispersion relations and extracting Hamiltonians. So here's one example of that. This is lanthanum copper oxide, very famous high-temperature superconductor. Here is the spin wave dispersion as measured with neutrons at a displacement source. You fit this dispersion relation to all the little tiny bumps and wiggles mean something, and you extract your magnetic Hamiltonian for the system in some detail. And like I said, this happens all the time. It's a regular occurrence. So here's a manganite, slightly different dispersion relation. You extract your different Hamiltonian. So the message here is then that if you can measure your spin wave dispersion in a momentum-resolved way, then you can lead directly to the Hamiltonian of your system, and that's what we care about. All right, so how are we going to do that? We're going to do that with inelastic X-ray scattering. So probably you're all familiar with this, photon in, photon out. You measure the energy transfer and the momentum transfer of the photon, and that's going to give you information about the dynamic properties of the material. So here's the X-ray cross-section. I imagine you've all seen this many times too. The first-order terms, these are the non-resonant terms in the cross-section, and the second-order terms, the resonant terms. The first-order terms give rise to very weak scattering. So if it's talking about an inelastic experiment, well, they need to look at something that's pretty strong, and that means typically a phonon. So a phonon, you've got one atom surrounded by its charge, you're wiggling it around, you're moving a lot of charge around, it gives you a relatively strong signal. So these experiments have been done for many years now using non-resonant inelastic scattering. And the typical resolution of a good spectrometer, Herix being an example, is something like 1 millivolt for non-resonant scattering. I'm going to talk exclusively today about the second-order terms, the resonant scattering terms. So they take your instant energy and you tune it to an atomic transition in your solid, to an absorption edge. These denominators become small, this term blows up, and it can dominate the cross-section. You get factors of 2 orders of magnitude at least enhancement in the scattering if you tune to an absorption edge. So this is strong scattering at this one magic energy. So this gives rise to resonant inelastic X-ray scattering. And this is strong enough that we can now look at very small, very weak excitations. We're moving one electron around, or we're flipping a spin or a fraction of electrons, something like that. So these are very powerful. It's a very powerful part of the cross-section. Until recently, the resolution was limited, and as I'll show you some history of that. But now the best spectrometers around sort of 30 millivolts type energy resolution is about the cutting edge right now, both in the hard X-ray and the soft X-ray regime. So there's some strengths and weaknesses to the technique, like everything else. One of the main strengths is you can look at very small samples, so it allows you to look at in a new system that's just been synthesized, for example. You only got a micron of stuff. You can still do an elastic experiment on it. You can work at high pressure or look at a surface or a thin film. There are very few kinematic constraints, if any. The multiple scattering effects tend to be weak. You can work in applied magnetic fields or in situ. It's a bulk probe. All these are good things. Limitation are the cross-section is complicated, particularly the resin cross-section. I'm just looking for Michelle, who's been doing a lot of work in this area. There's been a lot of progress over the years in understanding the resin cross-section, but it's still a complicated beast. It's still something you should think about each time you bring a new system into the experiment. And you need to find an appropriate resonance. You need to be a bit lucky to find the resonance that's strong and in an interesting system. We've been very lucky with the cuprates and with the irradiates in that regard. They're technically challenging experiments, and there are a few spectrometers around the world doing these, so it's hard to get beam time, and that's limited the growth of the field to some extent. So now here comes the kind of history part of the talk. If I take you back to the very early days, the first experiments in this field were done at Brookhaven at NSLS-1, so to speak, at X21. This was a beamline built by Chi-Chang Kao and motivated by Phil Platzman, who realized very early on that these resonances might be useful. So this is some of our very first data. This was actually the first data taken on a high TC. At the time, we had 2 EV energy resolution, so really terrible resolution by today's standards. And the scans were taking 24 hours a time to see something that maybe you believed was resonating here, sort of 6 EV. This, by the way, is one of these charge transfer stations I mentioned earlier. Around the same time, Peter Amonte, Zahida-san were doing similar work as we pushed the field along. It was obvious that that was not the source to do it on, and as soon as APS turned on and we got beamlines here, we came here. This is some of the early work that was done at Sector 9 with Thomas and Diego, looking at lanthanum copper oxide. So Young Joon Kim, who was a postdoc at the time, led this work. And now you see we've gotten 0.2 EV or 200 millivolts energy resolution. This is good enough now to start to see some details in the spectra. And we found this peak, and we watched it move and disperse as we went throughout the Brillouin zone. And so we interpreted this in terms of an exciton that was dispersing in the copper oxide plane. We may have been misinterpreting that. There are different explanations for that now, but the point was we were seeing details that we could never see before and beginning to ask questions of the cuprates that were interesting. So that was wonderful, and that was enough to motivate some of us to think about building a whole beamline dedicated to this kind of technique. So this was the birth of IXS-CDT, and I'm looking for Erjan, who was one of the prime motivators in this very early on, that we really should have a beamline just for this technique. So that was proposed and funded and built. And we built 2 instruments there, Merix and Herix. Merix was one dedicated for the resonant type measurements that I've been talking about. So Scott Coburn was the lead engineer on designing that. He did a beautiful job with this instrument, it's still on the floor today. And Yuri Shvitko was very early in the project. He was the one who really pushed to use a strip detector on the detector side. To be honest, we kind of resisted that. That seemed to be like a new idea. We weren't sure it was going to work. But it turned out to be that was like one of the big game changers in the field in terms of throughput of the experiments. It allows you to multiplex your detection scheme, so you're collecting more than one energy transfer at once, and that was huge. So Yuri gets the credit for pushing that idea, which I think originally came from the ESRF. Mohan was also very crucial early on in building the beamline. It was a big part of that construction effort. Thomas Tollner did the monochromator design for us, and Mary, Diego, and Thomas were all key in those early days. So just to kind of illustrate the progress over the years, it turned out there was one sample that got run on every single instrument as we built them out. It was copper germanate, which was interesting at the time because it was a one-dimensional cuprate, so we were curious about how it worked. And so we have a spectrum on each of the instruments on copper germanate, so I thought I'd put them together for you. So this was back in the late 90s at NSLS, where we had a count a second at 1.5 EV energy resolution. And we were pretty happy with a count a second, actually. That was strong for us. Then we came to Sector 9. You see the count rate went up by a factor of 6, and the energy resolution improved to 300 millivolts. So that's pretty rare to improve your count rate and your energy resolution. Usually you have to trade one against the other. And now you start to see these beautiful spectra with many details in that we could never pull out before. So as I said, that motivated the IXS CDT beamline. That was a sector 30 at the time. So again, another big jump as we improved the source and the upstream optics to 50 counts a second in the peak and just over 100 millivolts energy resolution. And the final step was this strip detector, which allowed us to put the analyzer closer to the sample, collect a larger solid angle, bumped it up to a factor to 600 counts a second now at about 90 millivolts energy resolution. So over the period of whatever this was, what's this, 8 years, if you take the figure of merit of an inelastic experiment as being something like the count rate divided by the resolution, it improved by 4 orders of magnitude. Anytime your experiment gets better by 4 orders of magnitude, you're pretty happy. And this was a really exciting time for us all as things improved so dramatically. And that hasn't stopped. Now I'm cheating a bit by adding on, oops, that's not there, the iridium work that Young Ho and company have been pushing. So the resolution has continued to improve, the count rates continue to go up, and the figure of merit for the beamlines have continued to get better. So it's really a strongly moving field. With these new improved resolutions and count rates, we started to look harder and harder at the materials we were looking at. So this is, again, lanthanum copper oxide with a new improved resolution, now at about 120 millivolts or so. And we're back to the 24 hours of scan now. We've gone back to let's really count it out and see what we can find. And here is this small bump that appeared in the tails of our elastic line at about 500 millivolts energy resolution. It took us a long time to believe this peak was real and to understand it, but it turns out what this was magnetic inelastic scattering. It's the first time it had been seen with X-rays. This is a 2-magnon peak, so you've done 2 spin flips to create this excitation. That was pretty exciting. And I remember sitting at the guest house watching the data coming in. It was so slow, there's no point in being in the beamline. But each time a 2-hour scan finishes, you add it up and you try and see, is the peak getting bigger, is it getting smaller? But it turned out to be a real peak. And so that was a big step for us to see magnetic inelastic X-ray scattering. It did have a downside because it proved that you have to be careful what you say in print. So this comes from an article that I wrote with Dune and Christian Berthier for a book that Denny Mills put together, trying to think about what third-generation sources would do. I don't know if you remember this, Denny, but in there we concluded that the possibility of doing inelastic magnetic scattering was remote at best. So that article came out about 7 years before we did the experiment. So the moral of the story is if you say something like that in print, make sure it's yourself who proves yourself wrong, not someone else. But of course, things have moved dramatically since then. Magnetic inelastic scattering is now, let's say, routine. Here is some more recent data. This is Young Ho Kim. That was the only picture I could find of you, Young Ho, online. I don't know if there's any other pictures, but that's what I found. So this is some gorgeous data that he and others took on strontium-2 iridium-04, and we'll come back to that throughout this talk. But what you see here, here's the elastic line, and you see these low-energy excitations are the spin waves. You see this beautiful dispersion, and the orbital excitations also disperse, it turns out, once you have the resolution to see it, which is a big discovery of this paper. And here is the peak energy as a function of momentum transfer. And you see now that we're really measuring a dispersion relation for the first time in some detail, and that allows you to extract the magnetic Hamiltonian. And just to compare X-rays to neutrons for a second, this left-hand plot is the data I just showed you. So this is resonant inelastic X-ray scattering. Here is the peak position, and here is the intensity of the spin wave peak as a function of momentum transfer. And here's the same data taken for lanthanum copper oxide. So different materials, but you get the idea. You see that the intensity, which is the structure factor, looks pretty similar in the two systems. They're both spin 1, or there's both quantum antiferromagnets with spin or J of about a half, so they have very similar physics. So this is giving you some sense that the X-rays are measuring the same structure factor that neutrons are measuring. So that's an important point, actually. The other thing you might notice is the data is significantly higher quality with X-rays than neutrons. So the story I just told you was basically the hard X-ray story. Roughly in parallel with that, done by others, the soft X-ray community was also pushing their resolution down and down and down to the point where they could also see soft X-ray inelastic magnetic scattering at the copper L edge. This is some work that I was involved in, taken at the Swiss light source, and I show you this for a number of reasons. This is lanthanum copper oxide, the high-temperature superconductor. And what you're seeing here is the energy loss spectrum. Here's the elastic line. Here are the spin waves, the DD excitations, and the charge transfer excitations. So we're seeing the whole excitation spectrum I showed you the cartoon diagram of earlier. The phonons are buried in here, but we see the whole thing with X-rays. The other thing to point out about these data was they were taken on a thin film. This is a MBE film grown by Ivan Bozovic at Brookhaven. So these are 25 layers of lanthanum copper oxide, each 1 unit cell thick. So from 25 unit cells of material, we can measure spin waves. That's an amazing accomplishment and statement. If you count up the number of atoms we're scattering from in this experiment and compare it to neutrons, we're 10 to the 11 times more sensitive. Huge advantage in the cross-section. So the lanthanum copper oxide crystal is like as big as your finger. It weighs 40 grams. So that puts a real restriction on what you're able to do with neutrons. So if you have a resonance and you can do the experiment with X-rays, X-rays will typically win. OK, so that was my introduction. So now I'm going to tell you about the experiment that we did using time-resolved measurements. So why are we interested in time-resolved measurements? Why are we looking at what's interesting about non-equilibrium dynamics? So it's interesting from a number of perspectives. So what we're doing here typically is we take our system, we hit it with some pulse of some frequency. The experiment I can tell you about is a frequency in the infrared, so this will be 600 MeV. So we excite some excitation, and then we drive the system into some new state. And typically, these metastable states can be really interesting and different from what you can get to in equilibrium. So that in itself is interesting. It allows the possibility of controlling the state of the matter with these photon pulses. So you can drive something, for example, from being a metal to an insulator on a few hundred femtosecond time frame. Or maybe you can drive it to be a superconductor, or who knows what. So photo control of condensed matter is a potentially really exciting avenue of research. And then the other motivation is that in many of these systems, there are lots of different ground states that are nearby in energy. And they compete with each other, and in equilibrium, one of them wins. But you don't really understand what's happening there, why that one won as opposed to the others, because they're all equilibrium. But if you can knock them out of equilibrium, they each have different timescales by which they would recombine, then you might be able to understand that ground state in the first place, how it came to that ground state in the first place. So understanding these competing interactions with their different timescales becomes possible in the time domain. And for these kind of experiments, we typically require sub-picosecond kind of time frames. That's the timescale which things occur on. So to give you an example of the kind of thing that people are looking at, these are relatively old now, but this is a manganite in which the system was driven from an insulator to a metal by shining a laser pulse at it, again, happening on sub-picosecond kind of time frames. Here is one of the more exciting and controversial results, which is driving a system from being an insulator to a superconductor with an infrared pulse. This is a particular cuprate superconductor which has stripe order in it. I won't really go into details of this, but if you shine, so this flat reflectivity curve tells you that it's an insulator. As you shine your light on it, you see this dip that occurs in the 60 wave number type range. That's an absorption edge associated with the superconducting plasmons. So the belief here is you're driving the system superconducting by shining light on it. Really, potentially very exciting and not at all understood, which is the point. There are many things about these fast, ultra-fast transitions that we don't understand. How does this melting of this magnetic order proceed? How do you drive it from a metal to an insulator? What's happening to the magnetic exchange when you drive something from a ferromagnet to an antiferromagnet, for example? If you're driving something superconducting, or this transient superconducting state, does its excitation spectrum look like the same as the equilibrium superconductor, or is it different? How do we understand these metastable states? How do the orbital excitations evolve? How do the phonons evolve? All these are interesting questions that we have no idea about with the current technology, current techniques. And so the question is, more generally, how does the magnetic Hamiltonian evolve with time when you excite one of these systems? And again, if you understand the Hamiltonian, you understand your system. And so that's leading us, of course, to time-resolved inelastic X-ray scattering. If we can measure our spin wave dispersion as a function of time following one of these pumps, then we can extract the Hamiltonian as a function of time. And that would be really exciting and really new. So the system we chose to look at was this strontium-2 iridium-04 system. We chose it for a number of reasons. It's a spin-orbit coupled Mott insulator. It's a very interesting system in terms of its physics and why it's an insulator in the first place. It's a two-dimensional quantum antiferromagnet, just like the high-temperature superconductors. It has an effective J of 0.5. It orders around 240 Kelvin or so Néel temperature to form this three-dimensional ordered magnetic structure I'm showing here. Magnetic structure. I don't know if I said, but the crystal structure is the same as the high-temperature superconductors, lanthanum copper oxide. If you start to dope the system, weird things happen, much like the cuprates. You can get a Fermi arc. You can get pseudogap type behavior. There are even predictions that if you dope it in a particular way, you might drive it superconducting, although those have not been proven yet. And perhaps the biggest and most important reason is it has a really strong, bright resonance in the iridium L3. And so that makes it wonderful for these resonant inelastic experiments. So let me give you a conceptual picture of what the experiment was. So here's our strontium-2 iridium-04 plane. And what we're doing is we're pumping that plane with an emitted-infrared pump. So that's this pulse that comes in here. This is about a few hundred femtoseconds long in time. So that pump comes in. It's tuned to excite an excitation from the lower Hubbard band to the upper Hubbard band. So moving carriers into the upper Hubbard band. So you can think of this, if you like, as photodoping holes into this band, if that's the way you want to think about things. And then we bring an X-ray pump, an X-ray probe pulse sometime behind that pump. And that's going to tell us what's going to go on in the system. And we tune that probe, to the iridium L3 edge to take advantage of these resonances. We sit at 90 degrees and look at the scattering. We can look at the elastic scattering, and that tells us about what's going on with the long-range order in the system. Or we can look at the inelastic scattering, and that'll tell us what's going on with the dynamics. So that's the conceptual picture of the experiment. So the first set of data I'm going to show you is data taken with elastic scattering. So these data were taken at SACLA, the free electron laser out in Japan. And what I'm plotting here is the intensity of the magnetic Bragg peak. So this is sensitive to the three-dimensional long-range order as a function of time delay, where time 0 here is when the pump pulse arrives. And so you see the pump arrives, and so these are different fluences, different amounts of pump. And you see the intensity gets rapidly suppressed. So this is before time 0, strong magnetic Bragg peak, and a picosecond after time 0, that peak is gone. So you've destroyed all the magnetic long-range order. It's gone. And that happens basically in a time resolution limited way. So a few hundred femtoseconds, the resolution of the experiment is not good enough to see how fast that goes away. So let's say within a picosecond, it's all gone. If we look at the charge response, so we measure this with optical reflectivity, this is telling us something about the charge dynamics. We see, again, this very fast decay following the pump pulse. And then that recovers on a few picoseconds kind of time frame, something like that. So this is the recombination of the electrons to give you back something that it's not fully recovered, but close to the original state. And if we look at the magnetic peak, so now this is a very long time behavior of this same magnetic peak, you find that it does recover, but it takes a long time to recover. And that recovery time depends on the fluence, but it's of tens to hundreds of picoseconds. So we pump this pulse, this pump pulse comes in, we melt the magnetic long-range order, it disappears, and takes a long time to recover. And if I have time, I might talk about that recovery. It's interesting in itself, but I'm going to focus mostly right now on what's happening to the magnetism in this transient state where you've melted the long-range order. So the question is, what's happening to the spin correlations after you melt that long-range order? And so we want to do inelastic X-ray scattering to figure that out, which means we need to build an inelastic instrument and take it to an FEL. And that's not a small thing to do. This is a cartoon diagram of the instrument as it was out at the LCLS, silicon 333 monochromator, which gives us about 50 millivolts kind of bandpass on the incident side. The spherically bent, diced silicon 844 analyzer, which will diffract back onto our CCD detector. And we have enough bandwidth in the spread here to be able to take the whole data in one shot. So we don't need to move any motors at all. We can take it all with a fixed spectrometer. So that's a real advantage in these kind of experiments. So we, and this means Diego and Young Ho, took the experiment out from the old instrument at Sector 9, took it out to the LCLS, assembled it. This is shown here. It's the 1 meter version. This CCD, let me just put on the X-rays here. The X-rays come from this side of the photograph. The sample's sitting here, diffracted onto the analyzer, and diffracted back onto the CCD. And this is then cooled with a cryojet cooler from the side. So you can imagine this is a fairly complicated thing to set up. We have to set it up, calibrate it, test it, put the sample in, try and take data, and that all has to happen within a sort of 5-day, if you're lucky, 5 lots of 12-hour shifts of beam time. So really intense period to get this all working and any hope to get data out. We've had 2 runs so far, 2 different beam lines. This was just getting the spectrometer itself working and making sure we understand how to do it. This was the first pump probe beam time. And just to show you that it all worked, here's a reference spectrum taken from some strong elastic scatterer where we had about 70 millivolts energy resolution. So that's not as good as the best synchrotron beamlines today, but was pretty good for the first attempt out there. So we were very happy with that. And so here's one of the first spectra we ever took. This is the image straight from the CCD. And you see here's the elastic line, and you see this faint stuff off to the side. This is the orbital excitation. And so even in a few, I think this was about a minute accumulation, you could see the orbital excitation. So that was pretty exciting. And that now allows us to dream about looking at the magnetic inelastic scattering. So this is the first time we've done that, so let me show you that. So this is looking at the inelastic scattering at pi 0. This is a zone boundary point in reciprocal space. So for those of you who know reciprocal space, it corresponds to this point in the zone. That's right at the peak of the dispersion. So the spin waves have moved out from the elastic line a long way, out at sort of 200 millivolts. These are the spin waves, and these are the orbital excitations. So there are three traces in this curve. The blue curve is at negative time delay. So that's taken before the pump has arrived. So this is the equilibrium state of the system. The red curve is 2 picoseconds after the pump has arrived. Now remember, that's the time when all the magnetism has been completely destroyed. And yet we see the curves are almost identical. And the black curve is just the difference between these two. And so within the noise, those two look identical. So that's telling us that even though the long-range magnetism has been completely destroyed, the short-range spin correlations are sufficient to support spin waves, basically unchanged from the ground state. So that was intriguing. If we move to the zone center, so that now this is sitting down here at the so-called pi point, right at the very low energy spin waves here in the reciprocal space. These are the data we get at that point. So now we're looking at the very long wavelength, low energy spin waves. So again, these are the same color coding. So minus 50 picoseconds is the equilibrium. 2 picoseconds is after the pump, and the black is the difference. Out here, again, these orbital excitations look like they've fully recovered. So these excitations recover very quickly. No sign of change 2 picoseconds in, much like the optical reflectivity data I showed you. But now we start to see a change in the spin waves down at these very low energies. And so you see there's a suppression of spectral weight out at maybe 100 millivolts, and it seems to pile up down at the lower energies. So it's looking like the long wavelength spin waves haven't fully recovered 2 picoseconds in. If we take this difference curve and plot it as a function of time delay, and we don't have much data here, but we have 2 data points. Here's 2 picoseconds after the pump arrived and 10 picoseconds. You see that this difference is washing out. It's beginning to recover on a sort of 10 picosecond kind of time frame. So that's telling you that low energy magnons are now relaxing back to the equilibrium state with a time scale of about 10 picoseconds. So how can we understand this? So we tried modeling this. So this is the spin wave dispersion taken from Young Ho's paper. And we asked, if we start fiddling with this, can we make anything that looks like our data? So the first model we took was to just take this magnon dispersion, leave it unchanged, and uniformly broaden the magnons. And so the motivation for that was, well, we've got all these photoexcited carriers flying around. Maybe the magnons are scattering from those and losing lifetime and therefore broadening. That's in fact exactly what you see if you just heated the sample up. As you thermally melt magnetism, the magnons just get broader. So that's one model. The other model is to take some of this low energy spectral weight and just push it down to even lower energies. So we look at the broadening model. We find this difference curve. So here is negative time delay, same color coding. So blue is the equilibrium state, and red is the pumped state, if you like. And we find if you just uniformly broaden the magnon spectrum, you get a difference curve that's all negative, which isn't what we see in the experiment. So we can rule this out. So that's different, again, from what you would see if you just heated up a quantum antiferromagnet. You just see the broadening. We're not seeing that. So these spin correlations that survive in this transient state are non-thermal. They don't look like the regular short-range spin correlations that you see in a thermally melted antiferromagnet. So that's really interesting. We don't fully understand. So I should just show you the transfer of spectral weight. Here is the same calculation, but now we've just taken this weight below 100 millivolts and shifted it down. And now you see you do get this difference kind of curve like we saw in our data. So we can rule out the magnon broadening, but this transfer of spectral weight does look like it's much more consistent with our data. And so the picture here is that these long wavelength correlations are relaxing, but on a relatively long time scale, 2 to 10 picoseconds. The short-range correlations, the ones we saw at the zone boundary, which correspond to basically nearest neighbor, relax much faster. Those are high energy excitations, so that makes sense that they would relax much faster. The low energy excitations, which seem to support two-dimensional spin correlations, but not long-range order, relax on a much lower time frame. So that's kind of the message of this, this experiment. We used this ultra-fast mid-infrared pump pulse to melt three-dimensional long-range order. It melts very fast, within a picosecond. The charge response recovers pretty quickly, again, within 2 picoseconds or so, mostly. But we create this transient non-thermal state with these non-thermal two-dimensional spin correlations that seem to survive for maybe 10 picoseconds, something like that. And the three-dimensional long-range order doesn't recover until much longer, tens or even hundreds of picoseconds before that fully recovers. That's probably driven by the interlayer coupling of the system. And we've looked at the fluence dependence of that and find that it's linear with fluence, so that's sort of consistent with that model. The other message here is that these time-resolved RIX experiments are possible at FELs, and that's a really big step for all the reasons I've been talking about. It gives you an entirely new class of information about non-equilibrium phenomena. By able to measure these spin wave dispersions, extract the Hamiltonian as a function of time, that's a really powerful experiment. The kind of dream experiment you would love to do is look at these spin wave dispersions following an optical pulse, and you can tune the wavelength of that, and look at get a movie of the Hamiltonian as a function of time. You can actually see how these exchange interactions evolve with time. And the kind of experiment we'd love to do is look at one of these transient superconductors and ask how do their excitation spectrum compare to the equilibrium one. That would be really exciting. All right, so I have a few minutes at the end. I just want to say a few words about the future of RIX. And I'm going to be very careful here, having been burnt once, not to say anything that I'm going to be proven wrong. And if you'll forgive me, I'm going to start with NSS2, which I know something about. As you are all aware, NSS2 is a brand new synchrotron. It's been built over the last 10 years and turned on about a year and a half ago. We have a goal of having best-in-class brightness and flux from the far infrared all the way up to the hard X-ray. And we can debate where that crosses over. Here at the APS, it's 15 to 20 kilovolts, something like that right now, I would guess. It's a 3 GeV ring, 500 milliamps, 30-cell double-band achromat with an emittance of order half a nanometer radian in the horizontal, about 8 picometer radians in the vertical, which means we're diffraction limited up to about 12 kilovolts, something like that. The machine is performing well so far. We're very happy with it. Just this last month, we had 2 big milestones. We achieved stored current of 400 milliamps for the first time. This is with all the insertion device gaps wide open. We see interesting heating effects and instabilities. It's not something we can deliver to users anytime soon, but we're pretty happy to achieve that milestone. And in terms of what we were able to deliver to the users, we're now running at 250 milliamps top-off mode as a routine operations. This was the last 2.5 days of the last run before we went into shutdown. We had 2 trips in that time. That's a good 2.5 days for us. We're not quite at that level yet, and we're nowhere near where you guys are. We'd love to get there. Our reliability is right now about 90%, which is pretty good. So we're frantically building beamlines there right now. We have 11 beamlines that are under operations or construction, 7 taking users, and 17 more under development. And so the next 2 to 3 years, we'll finish those, and we'll have about half the rings filled out by about 2019. I'm not going to go through all these, but these are all on the web. You can look at, see what's coming and what's already there. But I want to focus on one beamline in particular for this talk, which is the soft inelastic beamline. So this is one that's under construction right now. It has a goal of having 14 millivolts energy resolution at a kilovolt, the copper L edge. That will be the best in the world by at least a factor of 2. First light early next year, and first users sort of maybe the fall of 2017, something like that. So this is an amazing beamline. Here's our experimental hall. The instrument itself is an enormous instrument. It's a 15-meter arm. I'll show you that in a second. And it's far too big to fit on the experimental hall floor. In addition, this needs to be vibration isolation, temperature control, all that kind of good stuff to achieve the very high resolution. So it couldn't sit realistically on the floor. So it's a whole separate building. And if any of you have ever been there, this building is, I've seen this building for years in drawings, and to see it in reality is just breathtaking. It's probably a basketball court size here, just this big empty floor. So it's going to be really fun to see it up and running. This is what the instrument will look like. So we have our mirrors, exit slits. The sample sits here in this vacuum chamber. You need to be able to scan in Q and energy, so this whole thing rotates around on a 110-degree arc at 15 meters away from the sample and has to achieve better than a micron stability on the detector. So it's really a very challenging instrument. But if it all works, and we hope it will, it's going to open up a whole other set of science that wasn't possible in the lower resolution instruments. So this is just a snapshot of some of them. I'm not going to go through all these, but we can dream of looking at superconductors, looking at heavy fermions, thin films, electron-phonon coupling. We will have polarization analysis on the outgoing detector arm, so that will allow us to look at or resolve magnetic and charge excitations. There's going to be a lot that we can do with it. To just mention some of the more exciting experiments that will be possible, these are the experiments in the cuprates. Cuprates are famous for being superconductors, but they also have charge correlations that look really interesting and are not understood, that seem to play in with the superconductivity in ways that we'd like to understand. This is a theoretical prediction of the spin wave dispersion as you move this. So this would normally just be a straight sinusoidal dispersion, but as you move through a wave vector that corresponds to charge order in the system, there are predictions for all kinds of fun stuff happening in that charge order wave vector. That's not a place in reciprocal space that works well for neutrons, so that experiment can't be done with neutrons. It can only be done with X-rays. And that's something that we'll be able to do at 6 with the best resolution in the world. And related to this, coming out of the same wave vector are charge excitations. These are some very noisy neutron data in a different system, nicolates, that have similar excitations. And you see this streak of scattering coming out from that charge order wave vector. You'd love to look at that in a cuprate. Again, not enough intensity with neutrons, something we can do with X-rays for the first time. One can imagine looking at more exotic excitations, so even the superconducting gap itself ought to be observable with these kind of resolutions. Let's say in BISCO, something like that. There are theoretical predictions for what the intensity distribution should look like with a soft inelastic instrument, and that's something we can go after for the first time with X-rays. What we get that APAs can't get is we get the bulk sensitivity. So APAs, which can measure superconducting gaps, and the symmetry of the superconducting gap, can only do it in a surface-sensitive way, so that means you have to cleave a sample. We'll be able to look at bulk crystals, which will open up all the other cuprates for this kind of measurement. And then there are all kinds of theories that predict new modes in high-temperature superconductors that may or may not be there. Again, with the kind of resolution that we'll have at 6, we should be able to look for these for the first time. So that's kind of the future, maybe in soft X-rays, to have a 15 millivolt type instrument at NSLS2. If we look in the hard X-ray regime, the group here is really pushing that technology. So there's a list of people here, Ayman Saeed and company are really pushing the analyzer technology to the next generation. So the red curve here is the current silicon 844 analyzer at the Iridium L edge. They've been working in quartz, where they can get down to 14 millivolts in the same geometry with a spherically bent analyzer, and about 9.5 millivolts in a flat geometry. So again, that's another big step from where we are today. And you can imagine the two instruments, the one at NSLS2 in the soft X-ray at 15 millivolts, and one out here at 15 millivolts in the hard X-ray, be a really great suite of instruments to have to tackle all these problems. It's not as simple as just swapping out analyzers. The instrument itself needs to be upgraded to get the required performance in terms of center rotations, things like that. But I think this is a really exciting development for the hard X-ray RICs here. Looking a little further ahead, one might start dreaming about going out to an FEL and doing an inelastic experiment at LCLS2. And this is a calculation I did for them a while ago now, where we're trying to understand what we could do there. The point about LCLS2 is it's going to run at several hundred megahertz, several hundred kilohertz, perhaps even a megahertz. And so now you're getting 1 million pulses a second with these 10 to the 12 photons in each. It's a transform limited source as well. So that means if you stretch the pulse out in time, you compress it in energy. This is something that was first pointed out to me, at least, by Dave Monkton. That will make an excellent inelastic X-ray source. You can throw away the need for having a monochromator at that point and just use your source as the monochromator. And that's another huge gain in flux. And if you go through the numbers, at least in one case, at the time, the Swiss light source was the best instrument around. It had about 100 millivolts resolution, and a good spectra was taking an hour and a half or something out there. If you go through this with certain assumptions, it's 50 milliseconds at LCLS2. So a huge gain in throughput. Of course, the first thing you do is try and make that hard on yourself. You try and improve the resolution. And so you might start dreaming about getting down to the 1 millivolt type energy resolution at LCLS2. That's the holy grail for inelastic scattering. That's about as good as you need to get for any of the type experiments you might dream about. So that would be really exciting. That's obviously a few years away, but not so far away. Okay, so that's about all I wanted to say. So let me just conclude. Inelastic X-ray scattering, it's a particularly powerful probe, particularly resonant inelastic X-ray scattering of excitations in condensed matter systems and others, particularly electronic excitations. The field, as I tried to show you, has advanced tremendously over the years I've been involved and others. and is now addressing fundamental problems in condensed matter physics, particularly strongly correlated electron systems. The next generation instruments at NSS2 and here will push that even further. We'll get to resolutions that are better than thermal energies, and that's an important criteria when you're looking at these very low energy excitations. And particularly high temperature superconductivity, I think, will be really impacted by these kind of experiments. And who knows, we may even answer the question about why it's superconducting. And then even further, free electron lasers offer more potential for the inelastic experiments, and in particular for doing time-resolved inelastic X-ray scattering, and this idea about getting a movie of your Hamiltonian as a function of time following one of these pump pulses.